Thank you for staying with us. So this is the last talk of the session, and I have the pleasure to introduce Quitzeh Morales from Oaxaca. He's at Universidad Pedagógica Nacional in CONACYT, and he's gonna talk about signature of a manifold with single fixed point set of an abelian normal group. Thank you, Quitzeh.
Thank you, Rita. Hi, maybe you don't know, but today in Mexico is Independence Day. So we are, there were a lot of parties yesterday and ceremonies. Just a comment. Okay. Well, this is actually this work. With this question was my my PhD project, you can say. But well, the research on this object has advanced very slowly, and I just tell you. This uses the Conrad-Floyd construction, and so I'll be explaining a little bit things similar to what Bernardo said. Well, but not for Lie groups, but for discrete, maybe infinite groups. So manifolds are not necessarily compact. So it's a discrete group, and we have a co-compact action. And if the quotient is Hausdorff, then the action is proper when the isotropic group of every point is finite. So that's the definition I am using. Okay, I don't know how to. Okay. Well, as Bernardo were saying, we have a fixed point set, and these fixed point sets are with respect to finite group actions. And well, these are submanifolds of the initial manifold, and they are equipped with the structure of an NK invariant tubular neighborhood, where NK is the normalizer of K in G. And then, well, then you can make this, you can make this a G manifold by taking the union of all the fixed point sets with respect to with the same conjugation class. So, and when one has this manifold decomposition, where M1 is a common boundary, and the thing is the common boundary has no fixed points of the group K. So one can continue doing this inductively. That was this can be put in terms of these adjacent families that differ by the conjugation class of the subgroup K. Here we obtain for this long exact sequence different kinds of sequences depending on the structure of the manifold. It is real, oriented, or complex. Well, but because this is an inductive construction, one should take the simplest case. Well, actually, this is not the simplest case. Bernardo said the simplest case is when K is a cyclic group. Well, I am taking K a normal abelian. So this tubular neighborhood is G invariant. And I am assuming there are no more fixed points out besides those of K. So M1 and the common boundary are free G manifolds, and MK is a free G over K manifold, or a free manifold with respect to the wheel group. Okay. So yeah, the long exact sequences can be arranged and then construct spectral sequences, but depending on the family, on the group G, well, the family can be infinite. Usually for co-compact action, this family is finite up to conjugation. So the sequence converges. So that's why I was asking Bernardo what happened in the Lie group case, because how you control the isotropy so that sequence can converge. I'll say a little bit more about that later. Well, it is known that every manifold with proper action of a discrete group admits invariant triangulations. This is work of Illman and Corpi, his student. Well, one can assume such triangulations are made with respect to this inductive decomposition. So the boundary is triangulated, the interior and the outside separately and compatibly. Well, so one can translate one can translate the case of the manifold for the case of an algebraic Poincare complex. In this case, we obtain this kind of diagram. This is the usual Poincare duality diagram. And well, for non-compact manifolds, one take homology with finite supports. This is well, these are Poincare duality identities, and when these equations hold, we call this an algebraic Poincare complex. Analogously, one can define the algebraic Poincare complex with boundary, just taking the second identity modulo the boundary. And okay, because we triangulated correctly, the boundary submodule is a direct one. So one can, well, one would like to change the context to put it in the context of Hilbert complexes, and use the index for self-adjoint operators. Okay, these were CG modules. And well, one can change the operator, the duality operator, to make it self-adjoint. And then one can complete these modules to Hilbert spaces, taking k-dimensional L2 chains instead of finite chains. And the differentials extend to bounded operators. Well, and we have this, the self-adjoint duality operator. These are finitely generated projective modules, Hilbert modules, or the reduced group algebra. So one, we will seek for an index in K-theory of this reduced algebra. So we have this, and now we have this new notion of a point carrier complex. And if the dimension is even, then its signature is the class in K0 of the reduced algebra, is the formal difference of the positive and negative projections of this operator. This signature is an algebraic Bordism invariant and generalizes the classical signature for closed manifolds, and simply connected or not. In the case of not simply connected manifolds, that was work of Mishenko. Study of the signature and the Bordism invariance using the this theory of the equivalent theory for surgery, that was the rearrangement of Poincare complexes. Now one can define the signature even if the manifold has boundary, but the signature is no longer invariant. Okay, so if you check, well, I'll explain here. There is for the signature there is Novikov's additivity. So if you split a manifold by a common boundary, then the signature of the manifold, that's a signature of a manifold without boundary, is the sum of these non-invariant signatures of the two parts. Kirby gave a detailed proof using the Mayer-Gattori sequence, but in order to suit this, to generalize this property, in our case, where we don't have reasonable cohomology, we need to reinterpret this algebraically if we want to extend it, the proof. Okay, so for the task, I wanted to talk about that is it is an ongoing work. I don't know when will I finish, but I have a sabbatical year starting in October, I think. So maybe I will be doing this. Okay. Well, doing only this. So one takes this the manifold and then the tubular neighborhood, and the rest of remaining part, which is free manifold. And with Novikov's additivity, one would have this expression, but one considers that the signature of M1 is the classical signature for free actions. So it is already, it's already reduced, and one need to express the signature of this tubular neighborhood in terms of the fixed point set and this group extension, or the group extension and and the corresponding bundle structure of the tubular neighborhood. So this bundle structure can be an unitary bundle or an oriented bundle or other version. So what happened with the tubular neighborhood? Well, I just changing the notation, not to write so much. So one has this G-module projection from the neighborhood to the fixed point set, such that the inverse image of any change in the fixed point submodule is K-invariant, and one has this commutative diagram where the action in the bottom row is free and is by the Weyl group. And also this the boundary submodule is a free G module. So analogously with the case of the Conor and Floyd fixed point construction, well, this module, well, we called it quasi-free. Well, I think the name was already somewhere. Well, so how, well, this is just the initial idea of how to determine the structure of this tubular neighborhood module, starting with the K action and the extension. So if one restricts the action to K, one has a K module structure on CV that it is considered like fixed or given, and one knows that this structure is not unique, and two such structures differ by conjugation by elements in the group G. But as K is normal, conjugation depends only on elements of the Weyl group. So this change of representation depend only on the Weyl group. So one would like to define the structure of this complex solely only in terms of this data. So that's the task. Well, so I will give some kind of, some sketch of the proof of Novikov's additivity. This is a sketch. Actually, I told a little bit of lies. Actually, when we were checking about the different definitions of signature with Noé Bárcenas, we observed that actually this, that one actually cannot define from the beginning the Hilbert Poincare complex using self-adjoint operators. One has to stick with these signs, these signs in Poincare duality, and just at the end, when one wants to compute the index, and then one change the Poincare duality homomorphism for a self-adjoint operator. So the computations I will show should be made dimension-wise, and there's a lot of science involved, but for the sake of explaining, it's not necessary to deal with the science. So one has this sum of complexes that have this common boundary. This is a subcomplex that is direct summand. So the initial naive idea is to express this complex as the sum of these three complexes. Then one notes that taking the quotient eliminates EC1, and so E1 and E2 are actually these complexes, the complex with boundary, but with quotient by the boundary. So those are the complexes used for computing the signature, and in the case of manifolds with boundary. So one would write that the signature is the sum of these three signatures, and because this is a boundary, so this signature is 0, and then one gets this Novikov additivity. But this cannot be done directly because the decomposition is not a direct decomposition in terms of the operators of algebraic Hilbert Poincare complexes. So there's a lot of maps between different summands. So one should use another strategy. So the key ingredient in Kirby's proof of additivity is to use Poincare duality around the common boundary to construct a symmetric form. Well, this is the proof uses Mayer-Viatoris long exact sequence, and then constructs a symmetric form, and because it is symmetric, it has 0 signature, and that form is the form around the boundary. Well, this corresponds with a proof of Bordism invariance using homotopic symmetric complexes. Homotopic algebraic chain homotopy chain homotopy complexes have the same signature. This is there's this series of papers that Noé mentioned of Hickson and Rowe about mapping surgery to analysis. There's the proof, for example. But this is a sketch of a proof that, even in terms in algebraic terms, so this is the diagram. One has this diagram for C1 for any complex with boundary, where S is the Poincare duality homomorphism, and one can add the rows. These rows are exact, and one obtains this exact sequence, and one can express this sequence in terms of the decomposition for C1, and rearrange the terms, and then one has this diagram, and this the chain complex on the right, it's not the boundary, happens to be a chain complex with this differential, where where these B, S, and B1 are restrictions to the corresponding to the boundary operators and concurrent duality homomorphism or operator. So and this becomes a Hilbert Poincaré complex, an algebraic Hilbert Poincaré complex, using the isomorphism that exchange the two copies of this E1, and there is this kind of diagram that gives a homotopy equivalence between the complexes. So the thing one should do is to take this homotopy and to extend the homotopy to the whole complex. Is the one at the beginning in this sum. And then this makes sense of equation 2. So this will be the algebraic analog of Kirby's proof. This is a sketch. I still have to check the details. So when this gives Novikov, if it is successful, this gives Novikov's additivity. But what about the remaining the tubular neighborhood? So well, I think, well, I was checking yesterday some papers of Luke, where they compute the K-theory of reduced algebra of semi-direct products for some cases. It seems like it's a difficult task, and it doesn't, well, the examples I saw, they don't apply to this case. I have to study more about the known examples. Maybe when one could just express K-theory in terms of the group extension for some cases, and that would be some kind of expression for the signature. But without that, what one can do is to proceed by analogy, treating the fixed point submodule CMK as if it was the boundary. Well, this is not n-1 dimensional, but it is a direct sum. And in Kirby's proof, one has this Poincaré duality homomorphism. In this case, one has the K action. So what one could expect, maybe this is just an idea, is to, well, when one has this decomposition, well, different decompositions of the, one has this initial decomposition as G modules, but then one has these decompositions as K modules. So one could take this module, taking the sum of all the K modules, and then, well, then give a reasonable structure of G complex to this complex. So that would be that could be and in seek for a homotopy between the initial the 2 complexes. So that would be that some kind of reduction. Then after that one would have to express this in, well, these are the complexes. Then one has to write the operator and express the signature operator in terms of this new complex, and that would be a reduction of the signature for this case. So this is the subject I will be working in the next few months. I hope it was successful. And well, that's it. Thank you.
Thank you, Quitzeh. Are there any questions from the audience?
Well, I think there are no questions. So
well, we thank you again, Quitzeh, and we thank all the panel, all the speakers of this session, and all the participants. We appreciate you being here and asking questions, generating discussions, and I don't know, maybe I'll stop the recording. Well, unless Quitzeh wants to say something before. And we can stay for a bit for more discussion if you want to.
No, I was just saying that you can continue the previous questions to the other speakers.
Yeah, no, I'm sorry. I'm sorry I interrupted. But
no,
well,
no.
Thank you, Quitzeh, and thank you everybody for being here.
Thank you.
Thanks for